forget. This will be recorded and available on the iGuide website shortly. And with that, official welcome to everybody. We are here in our VCO series where we are highlighting the work of the UCGIS community champions. These are individuals this year who have been selected to be able to have their GeoAI expertise communicated to the iGuide community, and in this way, the UCGIS community as well, and be part of the group mentoring those people participating right now in our Spatial AI Challenge. So with that, I'm going to turn this over to Yingjie. This is a regular Zoom meeting, so please keep your own microphone muted, and we will have an opportunity to have question and answers at the end of this. Okay.
Okay. Yeah, thank you very much, Diana. It is my great honor to present this UCGIS Community Champion project supported by iGuide. So I will start to share my screen now.
Looks good. Thank you.
Okay. So the title of my presentation is Extracting Location Descriptions from Disaster-Related Messages using Geo-Knowledge-Guided Large Language Models. So, firstly, some background about this project. Social media platforms such as Twitter, or nowadays also known as X, have been increasingly used by disaster victims to request help and share urgent information. So here we have two tweets from the 2017 Hurricane Harvey. The first tweet says, #Hurricane Harvey, family needs rescue at this door number address. Two elderly, one is 90, not steady in her feet. The other one says, help, a pregnant lady is stuck in her car on I-45 between these two exits, #Harvey. If we can correctly and efficiently extract these location descriptions, we may be able to help disaster responders reach victims more quickly and potentially save lives. So existing research on location description extraction often used off-the-shelf named entity recognition, or NER tools. What an NER tool does is that it basically takes a piece of text as the input and outputs different types of named entities. So if we have a text message such as donations to the Red Cross have provided help for people in Texas impacted by Hurricane Harvey, an NER tool will be able to tell us that Red Cross is an organization, Texas is a location, and Hurricane Harvey is an event. So one approach we can do is to basically keep location in the output and disregard other types of entities. So this approach can indeed extract some location descriptions, such as city names or state names, but it also has two major limitations. The first limitation is that the extracted results, they are separate entities, not complete location descriptions. So if we look at these two example tweets again, for the first tweet, this door number address will be extracted as three separate entities, Grant Street, Cypress, Texas, instead of one piece of complete location description needed to perform geocoding. Similarly, the second location description will be extracted as three separate entities instead of the highway segment. This has a serious implication from a disaster response perspective, because if we mistakenly geolocate the victims to the center of Cypress, or even to the center of Texas, we can be wasting very valuable disaster response resources and time. Another limitation is that existing NER approaches, they cannot further differentiate these location descriptions into categories. And knowing the specific category of a location description, such as door number address, highway segment, or highway exits, is very critical for us to choose the suitable geolocating technique. Theoretically, both limitations, they can be overcome if we create a new data set with complete location descriptions instead of separate entities labeled. And we also label out the categories of these location descriptions. However, there is a lack of data sets labeled in this manner. With the emergence of large language models, we thought about maybe we could harness the power of large language models to address this challenge. So for large language models, such as generative pre-trained transformer or GPT models, we know that they are pre-trained on a large amount of data, and they can be adapted to a specific task through few-shot learning and sometimes even zero-shot learning. So they may have the ability to help us overcome this difficulty of lacking properly labeled data sets. However, in our preliminary experiments, we found out the default output of these models, they can be incorrect or inaccurate, likely because these large language models, by default, they do not really understand the location descriptions used by people under disaster contexts. So in a recent work, we proposed the Geo-Knowledge-Guided GPT Models. We proposed to use geo-knowledge about location descriptions to guide the output behavior of GPT models. So we fuse these two components, and the result is a fused GPT model that can take a piece of text message as the input and output, firstly, the complete location description, and secondly, the category of this location description. So we can look at the first component, the geo-knowledge part. So for the geo-knowledge part, in this work, we are using geo-knowledge about location and typical location descriptions we obtained from our previous study, in which we have identified 11 typical categories of location descriptions used by people under a disaster context. And then we fuse this geo-knowledge with GPT model to guide its output. We do so by embedding examples of different categories of location descriptions in a prompt, which is basically a series of instructions to the large language model. So in the prompt, we give multiple examples. For each example, we give a piece of input text message. For example, Papa stranded in home, water rising above waist at this door number address here. And we ask the model which part of the sentence represents location description, and then we give it an example answer and also its category here. And at the end of the prompt, we give a new message, and then we ask the GPT model to infer the location description and also its category in this new message based on the examples it has seen previously. Okay, so this is the general idea of this method. More details, you can see it in our paper. For this community champion project, I have shared two resources on the iGuide platform for this project. The first part is a test dataset, which contains 1,000 tweets from Hurricane Harvey, which are manually labeled with location descriptions and also location categories. We also carefully revised some of these tweets to remove some sensitive information to protect the privacy of the people who post these messages. They contain 11 location categories, and the URL of this data set on the iGuide platform is provided here. So if we click it, okay, so we can see this data set shared on the iGuide platform here. So another resource I shared on the iGuide platform is the Jupyter Notebook, which contains the code for doing mostly 3 parts of work. The first is to read these 1,000 disaster-related text messages. And the second part is the core part, which basically it will create the prompt and embed these examples in the prompt. And then finally guide the large language model of OpenAI through its API. And the third part of the code will perform some evaluation of the results. So here we can also take a look at the Jupyter Notebook here. Okay, so this is the Jupyter Notebook. Yeah, one thing I really like the iGuide platform is that when we see this notebook, we can directly run it, and then it will automatically start a virtual space on the iGuide platform, and we can run this Jupyter Notebook. Okay, so now this workspace has been created. You can see multiple folders here. The data folder contains the 1,000 text messages from Hurricane Harvey. So if we double click it, and we can see this data set here, it basically contains the text messages and also the ground truth annotation. So annotation provided by human annotators. So on the right side, we have the code. So the code currently is primarily designed for using the API from OpenAI. So in order to run this code fully, you will also need an API key from OpenAI. Once you have the API key, you can insert it here, and then we can run them. So the API of OpenAI is not free, but I consider it as affordable. For 1 million tokens, it's about $2.5. However, if you don't want to use the API from OpenAI, you can also choose to use open source large language models. And I will talk more about that later. So here, I will run some of the cells that do not require the OpenAI API. So we have, so firstly, we have some of these packages loaded here. And in this cell, it contains the prompt that we created that contains the examples about the typical location descriptions to guide the output of the GPT models. So you can see that we provide different sentences and we provide example answers. For example, this is category 1, and then a location description here. So in total here, we have 22 examples. And basically, we have 2 examples per category, 11 categories in total. Okay, and then we can, this is the function that will help us load the 1,000 Harvey tweet data. So this is a function to read the data. And then we can set some model parameters here. So depending on the model we want to choose, we can set different model names. Here, I use the GPT-4o model. But if you prefer to use other versions of model, for example, 3.5 Turbo, you can also set them. And the next function, this one is to basically get the location description recognition results from the large language model of OpenAI by calling its API. So you can see here, we are providing a new sentence. So the sentence that is not included in the examples. And we ask the model to infer the location descriptions in this new sentence and also its category. Okay, so then this is a test for running a single tweet. And generally, I prefer to start from simple and just try to run the code on 1 or 2 data examples to see if it works. If there is a bug, I can quickly catch it. And then if you have the OpenAI API, you should be able to get a result. It will show that it's category 9, and the location description is Rockport, Texas. And then here we basically set the path of the output result. So once the large language model processed this 1,000 tweets, where are the results going to be saved? So by default, the results will be saved in this result folder. And then this following code will basically run the query and then to get the processed results from the Geo-Knowledge-Guided large language model. So once this process has finished, it will take some time because you cannot, it has 1,000 messages, and also you cannot send out many messages in a very high frequency. But once it is finished, the result will be saved in the result folder. This is basically a JSON file. And this file is something I saved previously by using the GPT-4o model and running this code. So if you run this code again, using another version of your model, you may get another file created under this result folder here. So now we have get some results. How good is the performance of the model? So here we have code to evaluate the performance of the model. So we will check that we have the result file set to the target output. If you have a different output, you may want to reset this result file here. And we can read this result to see like how the result from our model looks like. It says don't have the pandas package installed, so I will quickly install it here. Okay, it's done. You can see it's very, very fast. All right, now we can run this code again. Okay, so now you can see the result from this file. Basically, in the output file, we have 4 major parts of the information. So the Twitter file ID and the full text of this tweet. And then the third column is the annotation. So that is these are the ground truth annotation provided by human annotators. And then for the last column here, we have the output from the model. So basically, what we can do is to we can compare the ground truth annotation with our model output to evaluate its performance. So in terms of evaluation metrics, we use the typical precision, recall, and F-score. Here we can first evaluate the performance of the model by looking at the text only. So here we are just looking at whether the model is able to extract these location descriptions correctly without considering whether the category is also correct. So here is the code for doing so. So we can run the code here. And then you can see the precision is about 0.7, recall is about 0.75, and F-score is about 0.73 here. So next, we can further look into how this model perform in different categories. So we have 11 categories. Now we want to look at not only just how good is models in terms of extracting those location description texts, but also the category. So now this becomes a more difficult evaluation, right? It's a more challenging task. The model needs to get not only the text, but also the category correct. So we have the code to do the evaluation here. So if we run it, so you can see the performance across different categories is here. So we can see that the model does pretty well for some categories. Maybe category 1, this is the door number address, and also in category 9, that is the administrative units. But the model also does not do so well in some other categories. Specifically, it actually completed and missed category 11. So this is a fairly complex category that represents a road segment between two intersections. So there's only a small number of these location descriptions in category 11 in the data. So if the model misses these location descriptions, it will not be able to get any correct result. So one thing about our code is that it also output some error analysis, which allows us to look into like how this model makes some mistakes. So these analysis files are in the output folder. So if we look at the output folder, so you can see these files are just generated as we are doing this demo. So we can look into the file evaluation string not matched to look at those location descriptions output by the model, but does not match our true annotation. So if we open it and with an editor, okay. So here, since we are pretty interested in this category 11, so we will do a search of category 11. So let's see. Okay, so we can see this category 11 here. Basically, this is a message says Texas 249 northbound at Chasewood Drive and Loeta Road exit. So the true annotation is category 11. What our model output is that it output Texas 249 northbound as C3, which is highway, and it output Chasewood Drive as category number 2, which is the streets, and also it output Loeta Road exit as category 4, which is a highway exit. So we can see, in fact, the model does pretty well in terms of each individual component. But in this case, what we need is to connect them all together because we want to pinpoint the exact segment on this highway. So if we look back into our code, and if we look at our prompt here, and specifically, we can look into our example of this category 11. So the example we provided in the prompt is Highway 10 between River Road and 4th Street. So we can see there is some difference between the example we provided to the GPT model versus the actual sentence encountered by the model. So one way to further improve this is maybe we could look into this prompt and think about some possible ways that we can make this prompt better to address some of these error cases that we have encountered in our error analysis. Okay, so let's see. Okay, so next we can do some visualization to show the precision required F-score. So we can run our code here. And here I use the Seaborn package, so we will quickly install it. And then we can run this is precision. We first get a precision here, and then recall, and then we can run the F-score. So this is some quick results we can get by looking at the performance of the Geo-Knowledge-Guided GPT-4o model. Of course, you can also look into multiple models, and then you can plot them all together in one figure to compare the performance of different models. Okay, so let me go back to my presentation here. Okay, so can everybody still see my screen?
Yes, we can.
Okay, perfect. Yeah, somehow the camera disappeared on my side, so I'm not so sure. Okay, so now we have these resources. How can we move forward? I thought about three possible directions to move forward. The first direction is to improve the prompt. So as we have seen in the demo, the prompt is one way to inform the GPT model about the geo-knowledge. But there could be other ways that we can improve the prompt and help the prompt to better convey the geo-knowledge to the GPT model. Another possible direction is to look into the model. So in this demo, we have been looking into the model, the GPT model from OpenAI. But we can also look into some open source large language models, such as Llama 3.3 and also even DeepSeek. If this is something that you feel interested in, I would recommend the Ollama platform here, which really simplifies the process of deploying large language models in your own computing environment. There are tutorials about how to set up Ollama in your own computing environment. Overall, I found out the installation process to be pretty straightforward. However, the major challenge comes down to hardware. Because these large language models, they often require high-end hardware, GPU, probably even GPU with larger than 48 gigabytes of memory. So for individual students and also for quite some universities, it can be hard to have this high-end hardware available. So I think the iGuide platform and also the Spatial AI Challenge really provide this unique opportunity. If you want to, play with these large language models, then you have some of this hardware available. And lastly is maybe we could also improve the data. So the data I provided in this data source is tweets from Hurricane Harvey only. So we could say that it's possible one model may run well in the data from one disaster, but may not run so well on the data from another disaster. Or it could run well in multiple disasters, demonstrating very good generalizability. So if we want to evaluate the ability of a model to generalize across multiple disasters, we may need to have some data, some labeled data, across different disasters. And many of us know how challenging it is to actually create this labeled data. If this is something you are interested in, our group recently developed a data annotation tool called Dialog that can facilitate this data annotation process, mostly focusing on location descriptions. So you can also check it out. Okay, that is all. Thank you very much, and I'm happy to answer questions.
Thank you, Yingjie. That was great. I'm so glad that we were able to hear about your research and your involvement with the Community Champions program and the
Thank you,
platform.
Diana.
Well, I have a couple questions, but while we get started, please, anyone, feel free to put a question in the chat. And if you'd like, we're also happy to, if you'd like to ask your question directly, feel free to raise your hand and turn your microphone on as well. But Yingjie, I think I'd love to hear a little bit about your experience in using the platform and any of your reflections on how you think it might be helpful for you to be able to use this for your students, or rather for your students to use it.
Yeah. Thank you very much. Thank you very much, Diana. I feel like I should have known it a bit earlier. I think it's really easy to use. So currently at UB, we are teaching students also on Geo AI. One course that I primarily teach my students is AI for geospatial applications. You know, when we teach the deep learning models, we want the students to get some hands-on experience, but not every student have this high-end laptop to train these deep learning models, especially when we are dealing with remote sensing images. That's generally like a major challenge for many students. And of course, we cannot say, in order to take this class, you must first buy a good computer to do so. So previously, I have been mostly using Google Colab. But I found out that the iGuide platform actually is very easy to use. And also, I think like I shared in the demo, I think what is good is once you already have a GitHub repository set up, then we can basically tell students, right, this is the notebook, you can just run it from there, and each student will have their own session. So I also noticed that sometimes when I work and I stop and then come back again, so the original session is already disconnected, but then when I come back again, I can pick up some of the previous work that is left, which I think is very, very useful. So I think setting up this whole workspace is very convenient, which can be convenient for students, because previously our students, when we do it in Google Colab, they will need to download these files themselves. Right? They will need to download the data. They will need to create the folders themselves, create this workspace in Colab. And then next time when they connect it again, it's gone. So it's not that convenient for them to use. So I feel like this part, I think it will really facilitate the learning process for students.
That's really great, because that was a big motivation for iGuide itself. iGuide is funded by the National Science Foundation as part of its Harnessing the Data Revolution big idea. And in order to support geospatial data science and replicable and reproducible geospatial data science, the platform is really optimized for doing that. We have a hand, Sean. You'd like to ask a question, please?
Yeah,
Thank
hi Yingjie. Good to see
Hi,
you.
Sean.
Hope
Good to see
you
you.
in a couple weeks in AAG. So I'm
Yes.
sitting on my sofa here at home. So these are true kind of office hours. I really like the simple presentation of this. I know there's a whole paper behind, but to the folks at iGuide, I really appreciate the simplicity in the presentation. Okay, I have 4 questions. Let's test your memory here. Going from increasing low, simple to more open-ended. First question, I know this is in the paper. Can you say, so I'm going to ask my questions and then I'm going to test your memory. First question, can you say more about the categories? More about the categories. Second question, you touched on this a little bit, sensitivity to the examples that you give in your, the system prompt, right? That seems like it'd be highly sensitive to the examples there. Third question, getting perhaps a little more interesting. My underlying question here is the geo-awareness of these different models. How geospatially aware are they? Have you observed, right? And direct thing that you can observe here, perhaps, is if you swap out, maybe you haven't done a lot of experimentation with this, but between different ChatGPT models, do some perform better for this task? Implying perhaps some are more geospatially aware, which is always kind of an interesting question. How geospatially aware are these complex and often black box models? And then final question, for some potential future work, how about some multimodal integration where you're getting some income, you can get a certain distance from just trying to extract these different categories from these tweets, but now marry that with some other information that can either be, maps that are symbolically encoded so that you know something more about intersections and stuff, or it could also be images, kind of rasterized maps or something, right? Some multimodal, and maybe you probably have thought about this, but I'd like to, we have, with location data, you can always tie things together. So why not tie together what you're able to extract from these tweets with large amounts of other spatially located data, which, maps and images and perhaps even remote sensed images. Anyway, I'll shut up now. And you don't have to answer all those. I don't want to take everyone's time, but I thought I'd throw those out because they're on my mind. Thanks.
Well, thank you, Sean. I'm actually writing them down. I'm cheating here.
Cheating, you're cheating.
I'm cheating here, yes. Yeah, so these are all very good questions. So for the categories, we used the categories that we analyzed previously from Hurricane Harvey in 2017. So we looked into those typical categories. There are typical door number, address, road intersections, highway exits. We also notice, for example, adjacent neighborhoods, right? Sometimes people will say, is there somebody doing rescue in this area A, neighborhood A/neighborhood B, right? Indicating a larger area containing this adjacent neighborhoods. So basically, we manually looked into these tweets and then summarized these categories here. Regarding the sensitivity to examples, this is a really good question. So in our experiments, we tested different sets of examples. So we embed different sets of examples in the prompt and then see how the model perform. So a major reason that we call this approach as a geo-knowledge-guided approach instead of just future learning is that it's not a random selection of 22 examples from some other sources. These examples, they are selected based on our understanding of the typical ways people describe locations. So we did multiple sets of experiments. So we tried different sets of real tweets selected based on our this category system we have. We also tested that using synthetic tweets, basically not real tweets, but tweets synthesized based on our understanding of the typical ways, and so door number, address, and so forth. We also did experiments by just randomly select 22 examples without actually looking into the specific categories. And we found out that the performance of the model is very similar as long as we follow this category schema, and that is our geo-knowledge here. No matter the tweets are real tweets or they are synthesized tweets. However, if we randomly select just 22 examples there, the model performs much worse And also it will not be able to recognize some categories of location descriptions because a random selection will miss some location descriptions that show up less frequently there. So that's what we find. In terms of the geospatial awareness across different GPT models, we also tested in different versions of GPT models. So most of the experiments was done in early 2023. At that time, GPT-4, the early version of GPT-4 was just released. So we tested different versions, GPT-2, GPT-2, GPT-3, ChatGPT, and also GPT-4. And we use exactly the same geo-knowledge, so the same prompt to guide them. And we found out that if we use exactly the same geo-knowledge to guide different GPT models, newer versions of GPT models does perform better than older models in general, overall, but not inside each individual category. So this is something I also noticed in my most recent run. You can see the result I showed in the demo. That is based on GPT-4o. And we noticed that it performed better in some categories than earlier versions, but not so well in some other categories. So for example, this category 11, it completely missed it, but in our previous versions, the GPT-4 model are at least able to recognize some examples, although the performance is still not so good. So it feels like the models, they increase the overall performance, but because the large language models is fairly complicated, they might tune some parts and some other parts don't stop. Yeah, in terms of future direction to integrate multi-models, I think that's a very interesting direction. So thank you very much for sharing this thought. I feel like in this work, we are mostly just looking into extracting these location descriptions as texts and categorize them. We haven't really go to identify their spatial footprints yet, the points, lines, and polygons. And I think the other part, we can really use some multi-model, look into these maps and then see how our text description of a location description can be represented on a map. Yeah. Thank you very much. And look forward to seeing you in AAG.
Yeah, there'll be many of the group who will be able to see some of these ideas presented at AAG, and iGuide itself has a number of sessions and presentations coming up. Dr. Xiaowen Wang, I see you turned your camera on. Would you have a question for the audience and for Yingjie?
Thank you. Thank you very much, Yingjie. I think it was really nice. Your presentation is showing the simple workflow and you put it in action. I saw you did pip install. And thanks, Dana, for giving me the opportunity to pose a few questions here. So 2 questions. One is a philosophical question. This is to follow up what Sean was trying to, I think, probe there. So the question is, for these large language models, they're not created to do spatial reasoning. They're created to mixing up words in a probabilistic way. Now, you're doing this prompt engineering and the knowledge integration as an external input to the language model. So the philosophical question is how good and how best this approach could get to. And especially for your application domain, if we count on your approach, any sensitivity and the potential errors remaining would still be consequential. So that's the first question, is a bit philosophical. The second question is practical. Let's say, assume your approach would work. You have a study area, you have a few thousands of tweets, and you also had a really innovative annotator approach. Hopefully that will help the community to label more data. So based on your vision, how do we take this to the real world? What are the remaining steps in your vision to possibly organizing broader community contributions and inputs to really make this approach getting either implemented or tested in the real world setting? You have one study area, you move to a different study area, actually you would not need much more human labor intensive labeling work on otherwise to apply your approach. So what would be the roadmap to get us there so that this would be possibly even more impactful? Thank you.
Yeah, thank you very much, Sheldon, for these two very good questions. Yeah, for the philosophical question, yeah, I also found it difficult to think about how these large language models, they can learn spatial relations, because during the training process, they have been mostly looking into texts, right? Like all the text on the internet. So there may be some text and location associations on the web, such as in geo-tagged Wikipedia articles, right? So we know those Wikipedia articles, they describe a city, they also have some coordinates there. So they may learn some of these spatial relations there, but it can still be quite limited. So I feel for this part, if we really want to focus on this spatial relation, learning the spatial relations in large language models, I feel we can still keep the large language model architecture, but maybe change the way we train the models, right? It's like NASA and IBM, they also have this Prisby foundation model, but they are not trained on text, they are trained on a lot of images. So if we want to focus on these spatial relations, maybe we could look into a lot of possibly automatically generated spatial relation pairs, maybe spatial distances, and then maybe mask some of these pairs, and then let the model to do some inference, and hopefully the model can learn these spatial relations. So I feel that is one possible way to help these large AI models to learn spatial relations. In terms of practicality, I think this is really something very, very important. Indeed, we wanted to ensure that our model eventually, in my case, eventually can be used by disaster responders. So I have been talking to disaster responders, disaster response organizations, and also emergency management in the Buffalo area. And one thing that is really interesting I learned from these conversations is that these emergency managers and also disaster response specialists, they really know a lot about this like latest technologies. I think probably also thanks to the AI trend. So they want to use a lot of like these new AI technologies, but they are also very resource poor. So in order to really use these like deep learning models, they need to have like high performance computers, and they also need to have like experts who know how to use this model, how to train, how to fine tune, and actually use these models properly. And they just don't have this much resource to actually deploy it. And when I was talking to them about this geo-knowledge-guided approach, they really feel that this is something that's quite promising, because basically the computing is actually done on OpenAI side, right? Computing is not done on the hardware in the emergency management center. It's actually done in the OpenAI side. And the emergency management part, they don't need to do much of this model training. So all they need to do is to focus on the knowledge part. So basically they focus on obtaining knowledge about how people actually describe locations under disaster context, and let AI people to actually handle it. So this is something they find promising, but they're also concerned about sending this type of information to a server beyond their control, because some these disaster some of the information on the disaster context is about the vulnerable population. So it's quite sensitive, and we have also been very careful in terms of trying to revise some of the message content in our data there. So they feel like if there are some possible approaches to host like a server in some trusted source, so maybe like a state on the source, and then that is something that they feel is more comfortable to use. So if we can really get there, I think looking at our approach, I think we could look into how the model performs in terms of some specific tweet context. So although all of these messages, they are describing locations, and some of them are describing it in a very urgent manner. So some of them are saying like, maybe the water is already rising, and it's just really, people's lives are threatened. So maybe we could first focus on these more urgent tweets as like a first goal, basically trying to achieve a more satisfactory level based on our discussion with disaster managers. And then hopefully this can become something that disaster managers will be maybe interested to adopt. So I think connecting with the actual disaster management practice and also with the disaster management experts, I think that's an important direction to move forward.
Thanks so much, Yingjie. Really appreciate your insights there. I think we might get additional questions. I don't want to take too much of your time here. I think your topic is not only important, but also popular. So, Diana, feel free to pick up.
Sure. Wednesday, I see you put your camera on. Do you have a question?
Hi, yes. Hi, Yingjie. Sorry, I missed, I think the first 15 minutes of your presentation, so I apologize if maybe you already covered this. But I'm kind of curious about the percentage of miscategorizations of this model, and whether or not you noticed perhaps any interesting like systematic miscategorizations or biases in the model, and what that can tell us perhaps about how this LLM is categorizing different cases.
Yeah, well, that is a great question. So yes, we looked into these mismatched or misrecognized results, and we do notice quite some interesting results. So I think I would say one major source of this mismatch is actually comes from the different perception of location descriptions. So I will give an example. So there may be like a road intersection described in the message, right? So somebody may say that I'm stuck at this road A and road B, right? So what we find out is that sometimes the model will recognize a slightly extended piece of the location description. So someone may say, I'm stuck at the intersection of road A and road B. The model will recognize intersection of road A and road B as an intersection. And but our human annotator will only annotate road A and road B as the correct answer. So if we directly compare the result from the model and also the human annotation, we will see this will be considered as an inconsistent match. So actually, this is, I think, a major source of this mismatch. And I think if we allow some sort of fuzzy match, so in our paper, we did some like supplementary experiments by allowing like a 75% fuzzy match, And we can see that the overall performance, I think it is increased to, I think probably about 0.85, and some categories even getting close to 100%, because there are some slight differences. But if we really look at the results, they are reasonable. The result is reasonable. So one thing I have been thinking these days is how we should actually evaluate the performance of these models in terms of recognizing the location descriptions or recognizing anything under a geographic context that may be a bit fuzzy, because we often choose like one single ground truth, and then we compare our model output with the single one ground truth, and we get a result, right? But if this phenomena we are looking at may be a bit fuzzy, or maybe could be conceptualized from some slightly different perspectives and are still reasonable, then maybe we could have 2 or 3 annotations that are slightly from different perspectives, and then if our model output one of them, that is considered as correct. So I think that is one thing I noticed about these issues. The model do make some other mistakes. So like I think classifying some similar location descriptions mistakenly. So if one is talking about a road intersection, the other one is talking about a segment that also involves road intersection, then the classification could have an issue. So those are the things that we can look a bit more and then see how we can improve it. Thank you, Wenfei.
Thank you.
Any other quick final questions for our presenter today?
Hi, I have a quick question. So yeah,
Okay.
thank you. Yeah, so I was just wondering if you have any future plan to deal with the voice data.
With the voice data? Oh, that's interesting. So do you mean voice data from the phone calls of victims? Yes. So victims, they call the center and then look into. Yeah, I think that could be an interesting direction. So I think the major challenge is that if the individual, they can really call the for example 911 or other rescue center. Typically, these rescue centers, they can get the GPS location of the individual. So in other words, we don't need to actually process the voice data. We can directly get the coordinates of the individual. In our case, we are looking into social media data because in major disasters like Hurricane Harvey, some of these 911 call centers, they were damaged. And meanwhile, there's like a huge number of people calling 911 at the same time. So many people, they actually cannot get connected to the 911 call centers. So they cannot call, they cannot get connected to the people they need help. So they cannot, then they try to look into other possible channels to seek help, and social media comes into their mind. So that's how we begin to see a lot of like this social media seeking help conditions, seeking help messages, and that's how we look into them.
Thank you.
Sure.
Thank you again, Yingjie. I'm glad there's been so much interest in this. Again, he is one of our community champions. I'm going to put in the link in the chat to the iGuide Community Champion Program. We have 3 other individuals this year too who will be giving VCOs. We've had one of them. There'll be 2 others. So we really much appreciate their contributions to iGuide's activities. And in another month or so, we'll begin to have information back from our 8 different groups participating in our Spatial AI Challenge. So thank you much, everyone, for joining us today. This recording will be processed and put on the website along with all of our other VCOs. And stay tuned. We've got a steady stream of them coming up in the future. Thanks, everyone.
Thank you, Diana. Thank you, everyone.
Yeah. Bye-bye.
Thank you, Diana. Thank you, Yingjie.